For state space systems, we defined the idea of state feedback, which was defining a control U such that it was proportional to the state with some gain matrix K. And this explicitly made the closed loop system follow a dynamic that looked like A plus BK times X. And this explicitly makes the state X go to 0. So this is the idea of stabilizing the state X. In many control problems, especially when we consider what we've already done with transfer functions, we're interested in the problem of tracking, which is the idea that we want some reference Y, our output Y, to go to some reference value R. And so a lot of what we're going to talk about for state space systems is really about the step response. And so we're going to think of R as being a constant value. And so we're interested in that output Y to essentially track that constant value R. So if we remember that Y is just C times X, then if Y is going to be the reference value R, then that means that X has to become something other than 0 in order to make Y equal to R. And so that special X value that makes Y equal to R is X star. So we're going to define X star such that C times X star is equal to R. So that's the idea. And it's intuitive then to define a control law, U, which looks similar to state feedback, but now has some extra terms. And the idea here is that the gain matrix K multiplies the difference between where we are in state space and where we want to be. So X star is where we'd like to be, because that would mean that we're actually making Y equal to R. And so the feedback then is going to be proportional to our deviation away from this desired point in state space. It's also important to realize, though, that inherently, without any control, if we design this feedback matrix appropriately without any extra control, this is just going to drive X to 0. And so for that reason, there may be some required amount of nominal input, which I'm going to call U star, that's required to keep the state at X star once it actually reaches there. Because notice, once X is equal to X star, this term here is equal to 0. And then this piece is not going to contribute anything to the control U. So we may need some amount U in order to keep the system there. And so actually, this can be found just by solving the system of equations. So if we want the state X to be X star, and we want it not to move from that point, that means that X dot is going to be equal to 0. And so if we just set that equal to our state equation here, then the amount X star, the value of X star that makes Y equals to R is given by this set of equations where Cx star is equal to R, just like we said before, and Ax star plus Bu star is equal to 0 because we're setting the state, the change in the state to be 0. And we can set this up as a system of equations and put it in matrix form. And then we can simply rearrange this using the inverse of this matrix here in order to show that X star and U star are going to be values that change depending on what R is. So if you change R, then that's going to change X star and U star. So we can write X star and U star in terms of the reference value R. And so if you did this matrix multiplication and inversion, you'd find out that this would be the exact value here and here. But more importantly, it's just that we can represent X star and U star in terms of the reference R. And so if I let N1 be this big matrix and N2 be this value here, that I can rewrite this original equation up here in terms of X star and U star. I'll substitute those in, and I get the fact that I can write the same control law in terms of Kx, and then another term that's another K times the reference. This Kr aggregates essentially the two terms N1 and N2. And then what's nice about this is this allows us to have a feedback control law that essentially uses all the knowledge that we already built for state feedback, which is the fact that U is equal to Kx. But then we're going to add one more term, And this can be interpreted as a feed-forward term. And so now our job for tracking is simply to find this k sub r. So again, in the last slide, essentially the whole purpose was to show that we can write our control law for tracking in state space in this form, which has a piece that's from essentially state feedback. And the role of the gain matrix K is to stabilize this matrix, closed loop matrix, A plus BK. And that's its only job. And then we can find the value of KR, which is another gain, and its entire job is to ensure that the output approaches the reference value that we want in steady state. And so we're going to essentially do the exact same process that we did on the previous slide, but now for the purposes of this form of a control law. And so we're going to set the derivative of x to be 0 because once we're tracking r and we're actually at that state r, then we want to stay there. And so we're not going to move the state, so the derivative should be 0. And we're also going to make sure that y is equal to r. And so if we solve this simultaneous equations, we can find what the value of x star is, essentially what the value of the state is when we are properly tracking the output y, and that output is tracking the reference r. And now we've substituted in what u is, and so now it's simply in terms of x star and r. And so from this first equation, we can solve for x star, and that gives us this expression in terms of the reference. And then we know that the x star times c should be equal to r. And so we just plug in this into x star. And the handy thing here is that the reference cancels out on both sides, and all we're left with is an equation that we can solve for this kr term. And so we can solve for kr, and the way to interpret this is that kr is a gain that is a feed-forward gain. And in the block diagram, you can see that kr sits right here, which is outside the explicit feedback loop. But it shapes the reference such that the state feedback can then be just responsible for stabilizing. So state feedback here is just responsible for stabilizing x, and then we shift where that stabilization of x to 0, we shift it over so that now you stabilize to x star, which is the same thing as making y track r. As we have seen, the idea of building a feed-forward gain into the controller has a lot of advantages. At the same time, it has some disadvantages. And the disadvantages are that if you have any uncertainty in the model, then that means that you're going to pick KR with some uncertainty. And that means that it's not going to be precisely accurate. And so that means that the result of your tracking problem is that it's not going to track as well as you would like if you design it with uncertainty. And so this is when we design a controller that has something like an integral component to it. And so now what we're going to do is take a look at how we design a integral controller within state space. And so we do this by augmenting the states. We add a new state z, and we define z dot, the change in z, to be exactly the error, the tracking error. And so if z dot is 0, essentially z approaches a constant value, then we can say that we're perfectly tracking the output y because z dot is equal to 0. So I can rewrite y in terms of cx, and I can plug that in and create a system of equations where my new augmented state is all the states that I have in x, and then the auxiliary state z. And so I combine a larger matrix given by this, which is essentially just rewriting these two terms, and this r finds its way into a new vector over here to the right. And we still have the control input u. And so now our job is to design a controller that incorporates all of these features. And so if you look at what the value z is really the integral of the error. And so this is what we'll use multiplied by a gain, an integral gain, in order to add it to the controller. And so if we can add that to the controller, just given our current state feedback kx, and then add on another term that is another gain times the integral of the tracking error. And then if we want, we can also include this kr times r term that we have from tracking. We'll see that this is actually not even important once we have this integral term that does the job of tracking all by itself. But you certainly, if you have information about what this feed-forward gain should be, then you can certainly use it. And another way to interpret this is that you construct a new gain matrix, which is essentially the composition of the existing gain matrix and the integral gain in the context of the larger state x and z. If we substitute in this new definition of our controller, u, into our new augmented system, this is our open loop system where we haven't plugged in what u is. And so if we now plug u, the definition of u, into this, then once you simplify these matrices, you get the closed loop system. And the closed loop system is this xi variable, which is essentially just the augmented state. And now you have the closed loop dynamics matrix that you get from state feedback, and a piece that comes from the integral gain. And then there's also a piece that comes from the reference. And so now the way that we can interpret this is that you have this xi dot equal to this new A matrix, dynamics matrix, times the state, xi, plus this new input matrix B times the input signal. And now, just as we've interpreted with transfer functions, the quote-unquote input to these systems, the signal that's coming into the closed loop system, just like this is the whole closed loop system together, and the signal that's coming in is the reference R. And so R plays the role of the input, where U played the role for the input when we dealt with open loop systems. And so now, one of the things we can do is we can assess the steady state error of this state space system by letting xi dot equal to 0 and solving for what the xi value is that will solve this problem. And so if R is a step input, then just like one of our homework problems, we can now solve this by essentially finding the inverse of this new A matrix A bar and multiplying it by that B bar, just like we did in that homework problem. This gives us a value for xi star. So that means that in steady state, this xi star limits to a specific value. And this means that if xi dot is equal to 0, and one of those components of xi is z, that means that z dot is also equal to 0. And that's really our objective, because remember, z dot was equal to r minus y. So that means that now r is equal to y, so we're tracking the reference. The output is actually tracking the reference. So just by integral feedback alone, using that in the state space system, we can achieve tracking. That's even true if you set this term equal to 0. So even if you don't know kr well, or if you don't know it at all, you can set this term equal to 0, and that will still allow you, setting this whole term to 0 will still allow you to achieve the same result, that a step in R will lead to a constant change in xi, which we can find as xi star. That means that xi dot is actually 0, which implies that z dot is 0. So again, you don't need this feed forward term, but again, if you have it, then you can certainly use it.